There are 4 different types of quantum numbers that go into the Schrödinger equation. They tell us the address of an electron within the atom. I'm going to use the address from Finding Nemo as an analogy. P. Sherman, 42 Wallaby Way, Sydney. The principal quantum number n tells the size and energy level of the orbital. The principal quantum number is the most general, like Sydney, Australia is in our example address. The angular momentum quantum number L tells us the shape of the orbital. It is more specific and depends on the value of n, just like there are only certain streets in Sydney, and this specific one is Wallaby Way. The magnetic quantum number m sub L gives us the orientation of the orbital. This is even more specific, just like there are only certain house numbers on Wallaby Way, and this specific house is house number 42. Knowing n, L, and m sub L is sufficient to describe a particular orbital, just like knowing the address is 42 Wallaby Way, Sydney, is sufficient to find a particular house. If we wanted to write a letter, though, we would also need to address it to a specific person. We want P. Sherman, not Q. Sherman. In the same way, the electron spin quantum number m sub s addresses a specific electron within an orbital. We will look at each of these quantum numbers in more detail. The principal quantum number n corresponds to the n value in Bohr's model of the atom. Even though Bohr was wrong and electrons do not orbit the nucleus, he was right that there are certain integer values of energy levels. A larger value of n corresponds to an orbital that is farther out from the nucleus and is therefore larger. I like to think of the concept of Russian nesting dolls. n equals 1 is the smallest doll on the inside, n equals 2 is the next doll out that surrounds the first one, and so on. The energy levels that are larger are also higher in energy, so n equals 1 is the lowest energy, and the energies get higher as you go out. There are only certain allowed values. Just like in our address, there are only certain cities in Australia. In this case, the values will be integers starting with 1. In theory, the numbers could keep counting up to infinity, but practically speaking, atoms have only been detected with at most n equals 7 so far. There could be several orbitals within an energy level. All of the orbitals within an energy level are considered to be in the same shell. For example, there are 4 orbitals in the n equals 2 energy level, so they are all in the n equals 2 shell. The angular momentum quantum number L tells us the shape of the orbital. Each shape has both a letter and number designation. Spherical orbitals are called S and have 0 for their quantum number L. P orbitals are dumbbell-shaped, and their corresponding L value is 1. D orbitals are generally 4-leaf clover-shaped and have an L value of 2. F orbitals have a variety of shapes, which I will show you in a few slides, and they have an L value of 3. S is always 0, P is always 1, D is always 2, and F is always 3. If I were making up the numbers myself, I would have started counting with 1. However, remember, these numbers go into the Schrödinger equation to make the graph of the orbital, so they have to be specific values to match up with the observed shapes. Just like n has certain allowed values, so does L. The allowed values depend on n and range from 0 to n minus 1. This is just like in our address, where there are only certain streets in Sydney, Australia. The n value and the L value will never be the same as each other. The maximum L can be is n minus 1. So if n is 1, L ranges from 0 to 0, which means it can only be 0. The corresponding letter designation when L equals 0 is S. So there can only be spherical orbitals in n equals 1. When n equals 2, L ranges from 0 to 1. 0 is S and 1 is P. So in the second energy level, there are both spherical and dumbbell-shaped orbitals. When n equals 3, L ranges from 0 to 2. 0 is S, 1 is P, and 2 is D. So the third energy level has spherical, dumbbell-shaped, and 4-leaf clover-shaped orbitals. When n equals 4, L ranges from 0 to 3, so the fourth energy level contains s, p, d, and f orbitals. There can be multiple orbitals that have the same values for both n and L, so they would be considered to be in the same subshell. For example, there are 3 different p orbitals in the second energy level, and they would all be considered to be in the 2p subshell. Electrons and the orbitals that contain them behave like waves. Just like the 1D and 2D waves we saw earlier in the chapter, they can have nodes. For orbitals, the nodes are regions where there is a 0% chance of finding electrons. The number of radial nodes in an orbital is equal to n minus L minus 1. For a 1s orbital, the number in front is the n value, so n equals 1. S corresponds to an L value of 0. 1 minus 0 minus 1 equals 0. So a 1s orbital has 0 nodes. A 2s orbital has n equals 2 and L equals 0. 2 minus 0 minus 1 equals 1. So a 2s orbital has 1 node. That means electrons can be in the red region or the blue region in the figure, but not in the spherical sliver of empty space between them. A 3s orbital would have 2 nodes. Notice the size of the orbital increases from 1s to 2s to 3s because the principal quantum number is increasing. S orbitals are spherical and are therefore pointing in all directions at once. Because of their symmetry, there is only one possible orientation, so there is only one s orbital within each s subshell. P orbitals are dumbbell-shaped and can be pointed along the x-axis, the y-axis, or the z-axis. There are 3 different orientations, which would each be separate orbitals. So there are 3 orbitals in each p subshell. D orbitals are generally clover-shaped, with the exception of the dz squared orbital, which looks like a dumbbell with a donut around it. There are 5 different orientations, so there are 5 d orbitals within each d subshell. F orbitals have a variety of shapes. Most have 6 or 8 lobes, but one of them has some donuts. In total, there are 7 different orientations of F orbitals, so there are 7 F orbitals within each F subshell. Each orbital orientation has a corresponding m sub L quantum number. For example, px, py, and pz correspond to m sub L values of -1, 0, and +1. The m sub L numbers can only be certain allowed values that depend on the value of L. Just like there are only certain houses on Wallaby Way, there are only certain orientations possible for each shape. The allowed values for m sub L range from -L to +L. If L is 0, the allowed values range from -0 to +0, so that's just 0. It makes sense that there is just one allowed value for m sub L when L equals 0, because s orbitals have only one orientation. When L is 1, m sub L ranges from -1 to +1, so that's -1, 0, and +1. These values correspond to the px, py, and pz orientations. When L is 2, m sub L ranges from -2 to +2. It has a total of 5 different values, which correspond to the 5 different orientations of d orbitals. When L is 3, m sub L ranges from -3 to +3. So there end up being 7 different values corresponding to 7 different orientations of F orbitals. Again, if I were making up the numbers, I would start counting at 1, but these are the numbers that are necessary to make the Schrödinger equation work. This figure summarizes what we have already talked about with quantum numbers. The columns represent different energy levels with different values of n. The rows represent shapes with different values of L. The numbers in the boxes represent specific orientations with different values of m sub L. Each box represents one orbital and can be described by a combination of 3 different quantum numbers. For example, the leftmost box has n equals 1, L equals 0, and m sub l equals 0. Notice that each energy level has one new shape associated with it. There theoretically could be other shapes beyond F in the 5th energy level and beyond, but none of the known elements use them in their lowest energy configuration. How many orbitals are in a subshell designated by the quantum numbers n equals 4 and L equals 3? Is it A, 5, B, 7, C, 1, or D, 3? The correct answer is B, 7. One way you could figure this out is that when L equals 3, that corresponds to F orbitals, and there are 7 different orbitals in an F subshell. The other way to figure it out would be writing out all the allowed m sub l values based on the L, and then counting how many different ones there are. The allowed values would be -3, -2, -1, 0, 1, 2, and 3. That would be 7 different values, which corresponds to 7 different orientations. Which of the following is a legitimate set of 3 quantum numbers for n, L, and m sub l respectively? The word respectively here means that the numbers go in that order. The first number is the n, the second number is the L, and the third number is the m sub l. You will be using your rules for allowed values. Based on the n, the first number is the L allowed. Based on the L, the second number is the m sub l allowed. Is the correct answer A, 2, 1, and 0, B, 3, 3, and -1, C, 1, 0, and 2, or D, 4, 3, and -4? The correct answer is A, 2, 1, and 0. If n is 2, L ranges from 0 to 1, and 1 is in that range, so it is allowed. If L is 1, m sub l ranges from -1 to +1, and 0 is in that range, so it is allowed. B is incorrect because the L value is too high. The max it can be is 2 if n is 3. C is incorrect because the m sub l value is out of range. When L is 0, m sub l can also only be 0. D is incorrect because the m sub l value is out of range. When L is 3, m sub l ranges from -3 to +3, and -4 is outside that range. Our final quantum number, the electron spin quantum number, m sub s, tells us which electron within the orbital we are talking about. Remember, each orbital can hold up to 2 electrons. One of the electrons has an m sub s value of +1/2 and is called spin up. The other electron has an m sub s value of -1/2 and is called spin down. Notice this is the only quantum number that is not an integer. Each electron has a unique address. No 2 electrons can have the same exact set of quantum numbers. Some of the numbers could be the same. There could be someone living at 42 Birch Street in Sydney, or there could be a Q Sherman at 42 Wallaby Way, Sydney. But each electron has a unique combination of numbers, just like each person has a unique identifying address. And this is the basis of the Pauli exclusion principle.